What is calculus? A question many have asked. Calculus is a branch of mathematics focused on limits, functions, derivatives, integrals, and infinite series. This subject constitutes a major part of modern mathematics education. It has two major branches, differential calculus and integral calculus, which are related by the fundamental theorem of calculus. Calculus is the study of change, in the same way that geometry is the study of shape, and algebra is the study of operations and their application to solving equations. A course in calculus is a gateway to other, more advanced courses in mathematics devoted to the study of functions and limits, broadly called mathematical analysis. Calculus has widespread applications in science, economics, and engineering, and can solve many problems for which algebra alone is insufficient. Calculus has historically been called the calculus of infinitesimals, or infinitesimal calculus. More generally, calculus refers to any method or system of calculation guided by the symbolic manipulation of expressions. Some examples of other well-known calculi, the plural of calculus, by the way, are propositional calculus, variational calculus, lambda calculus, pi calculus, and join calculus. The history of calculus. In ancient times, some of the ideas that led to integral calculus were introduced. But, for the most part, these do not seem to have been developed in a rigorous and systematic way. Calculations of volumes and areas, one goal of integral calculus, can be found in the Egyptian Moscow Papyrus, circa 1820 BC, before Christ. But the formulas are mere instructions with no indication as to method, and some of them are wrong. From the age of Greek mathematics, Eudoxus used the method of exhaustion, which prefigures the concept of the limit, to calculate areas and volumes, while Archimedes developed this idea further, inventing heuristics, which resembles the methods of integral calculus. The method of exhaustion was later reinvented in China by Liu Hui in the 3rd century after Christ, in order to find the area of a circle. In the 5th century, Zhu Chongzi established a method that would later be called Cavalieri's principle to find the volume of a sphere. In the 14th century, Indian mathematician Madhava of Sangamagrama and the Kerala school of astronomy and mathematics stated components of calculus such as the Taylor series, infinite series approximations, an integral test for convergence, and early forms of differentiation. Term-by-term integration, iterative methods for solutions of nonlinear equations, and the theory that the area under a curve is its integral, obviously. The Yukti Bhasa, a book from this school, is considered to be the very first text on calculus. God bless America. In Europe, the foundational work was a treatise due to Bonaventura Cavalieri, who argued that volumes and areas should be computed as the sums of the volumes and areas of infinitesimally thin cross-sections. The ideas were similar to Archimedes in The Method, but this treatise was lost to time until the early part of the 20th century. Cavalieri's work was not well respected, since his methods could lead to erroneous results, and the infinitesimal quantities he introduced were disreputable at first. The formal study of calculus combined Cavalieri's infinitesimals with the calculus of finite differences, developed in Europe at around the same time. Pierre de Fermat, claiming that he borrowed from Diophantus, introduced the concept of inequality, which represented equality up to an infinitesimal error term. The combination was achieved by John Wallis, Isaac Barrow, and James Gregory, the latter two proving the second fundamental theorem of calculus around 1670. The product rule and chain rule, the notion of higher derivatives, Taylor series, and analytical functions were introduced by Isaac Newton himself in an idiosyncratic notation which he used to solve problems of mathematical physics. In his publications, Newton rephrased his ideas to suit the mathematical idiom of the time, replacing calculations with infinitesimals by equivalent geometrical arguments, which were considered beyond reproach. He used the methods of calculus to solve the problem of planetary motion, the shape of the surface of a rotating fluid, the oblateness of the Earth, the motion of a weight sliding on a cycloid, and many other problems discussed in his Principia Mathematica, published in 1687. In other words, he developed series expansions for functions, including fractional and rational powers, and it was clear that he understood the principles of the Taylor series. He did not publish all these discoveries, and at this time, infinitesimal methods were still considered disreputable. These ideas were systematized into a true calculus of fundamentals by Gottfried Wilhelm Leibniz, who was originally accused of plagiarism by Newton. He is now regarded as an independent inventor of and contributor to calculus. His contribution was to provide a clear set of rules for manipulating infinitesimal quantities, allowing the computation of second and higher derivatives, and providing the product rule and chain rule. In their differential and integral forms, unlike Newton, Leibniz paid a lot of attention to the formalism, often spending days determining appropriate symbols for concepts. Good job, Leibniz. Leibniz and Newton are usually both credited with the invention of calculus. Newton was the first to apply calculus to general physics, and Leibniz developed much of the notation used in calculus today. Which is superior? The basic insights that both Newton and Leibniz provided were the laws of differentiation and integration, second and higher derivatives, and the notion of an approximating polynomial series. By Newton's time, the fundamental theorem of calculus was known. When Newton and Leibniz first published their results, there was great controversy over which mathematician, and therefore which country, deserved credit. Newton derived his results first, but Leibniz published first. Newton claimed Leibniz stole ideas from his unpublished notes, which Newton had shared with a few members of the Royal Society. The fool! This controversy divided English-speaking mathematicians from continental mathematicians for many years, to the detriment of English mathematics, all thanks to Isaac. A careful examination of the papers of Leibniz and Newton shows that they arrived at their results independently, with Leibniz starting first with integration and Newton with differentiation. Today, both are given credit for developing calculus independently. It is Leibniz, however, who gave the new discipline its name. Newton called his calculus the science of fluxions. Since the time of Leibniz and Newton, many mathematicians have contributed to the continuing development of calculus. One of the first and most complete works on finite and infinitesimal analysis was written in 1748 by Maria Gaetana Agnesi, a woman. In calculus, foundations refers to the rigorous development of a subject from precise axioms and definitions. In early calculations, the use of infinitesimal quantities was thought unrigorous and was fiercely criticized by a number of authors, most notably Michael Rolle and Bishop Berkeley. Berkeley famously described infinitesimals as the ghosts of departed quantities in his book The Analyst in 1734. A recent study argues that Leibnizian calculus was more solidly grounded than Berkeley's empiricist critique thereof. Working out a rigorous foundation for calculus occupied mathematicians for much of the century, following Newton and Leibniz, and is still, to some extent, an active area of research today. Several mathematicians, including Maclaurin, attempted to prove the soundness of using infinitesimals, but it would not be until 150 years later, 15 decades, when, due to the work of Cauchy and Weierstrass, a means was finally found to avoid mere notions of infinitely small quantities. The foundations of differential and integral calculus had been laid. In Cauchy's writing, we find a versatile spectrum of foundational approaches, including a definition of continuity in terms of infinitesimals, and a somewhat imprecise prototype of Greek letters definition of limit in the definition of differentiation. In his work, Weierstrass formalized the concept of limit and eliminated infinitesimals. Following Weierstrass, it eventually became common to base calculus on limits instead of infinitesimal quantities. Bernhard Riemann used these ideas to give a precise definition of the integral Riemann values. It was also during this period that the ideas of calculus were generalized to Euclidean space and the concept plane. In modern mathematics, the foundations of calculus are included in the field of real analysis, which contains full definitions and proofs of the theorems of calculus. The reach of calculus has also been greatly extended. Henri Lebesgue invented measure theory and used it to define integrals of all but the most pathological functions. Laurent Schwartz introduced distributions, which can be used to take the derivative of any function whatsoever. Limits are not the only rigorous approach to the foundation of calculus. An alternative is Abraham Robinson's non-standard analysis. Robinson's approach, developed in the 1960s, quite recent, uses technical machinery from mathematical logic to augment the real number system with infinitesimal and infinite numbers, as in the original Newton-Leibniz conception. History repeats itself, my friends. The resulting numbers are called hyperreal numbers, and they can be used to give a Leibniz-like development of the usual rules of calculus. Calculus is used in every branch of the physical sciences: actuarial science, computer science, statistics, engineering, economics, business, medicine, demography, and in other fields, wherever a problem can be mathematically modeled and an optimal solution is desired. It allows one to go from non-constant rates of change to the total change, or vice versa. And many times in studying a problem, we know one and are trying to find the other. Physics makes particular use of calculus. All concepts in classical mechanics and electromagnetism are interrelated through calculus. The mass of an object of known density, the moment of inertia of objects, as well as the total energy of an object within a conservative field, can be found by the use of calculus. An example of the use of calculus in mechanics is Newton's second law of motion. Historically stated, it expressly uses the term rate of change, which refers to the derivative saying the rate of change of momentum of a body is equal to the resultant force acting on the body and is in the same direction, commonly expressed today as force minus mass times acceleration. It involves differential calculus because acceleration is the time derivative of velocity or second time derivative of trajectory or spatial motion. Starting from knowing how an object is accelerating, we use calculus to derive its path.